Hello dear students, welcome back. So we have discussed the structure of DNA in the last class. I think we shall proceed. Okay, so today we are discussing how DNA is packaged inside a cell. I think almost all of you have studied the structure of DNA. Okay, last year you have studied and this year again you have revised, and I think it is thorough, the structure of DNA is. So our today's topic is packaging of DNA. How is DNA packaged inside a cell or inside a nucleus? So the topic is DNA packaging. So in the last class we have discussed that the DNA, length of the DNA is measured in terms of the number of nucleotides, and also we have discussed human DNA is of about, the diploid content is of about 6.6 into 10 raised to 9 base pairs, nucleotides long. What is the length of human DNA? It's having a length of 6.6 into 10 raised to 9 nucleotide, or we can say base pairs. Okay, that's the length of human DNA. And what is the length of one base pair? One base pair DNA is having a length of 0.34 nanometer. You have studied 0.34 nanometer. When we convert it into meters, it is 0.34 into 10 raised to minus 9 meters. Okay, so in a total, in every cell of human body within the nucleus, there is about 6.6 into 10 raised to 9 base pairs of DNA. And one base pair is having a length of 0.34 nanometer. That means 0.34 into 10 raised to minus 9 meters. So what is the total length? Means we have to multiply this into this. So in one cell we have 6.6 into 10 raised to 9 into 0.34 into 10 raised to minus 9. Okay, so what happens? This 10 raised to 9, 10 raised to minus 9 cancelled. So our total length of DNA is 6.6 into 0.34. It comes about 2.2 meters. So can you imagine that? That means our cells, can we see our cells with our naked eye? No. Can we see our nucleus within the cell? So cell itself is micrometer sized. Within the cell, within the nucleus, the DNA is meters long, 2.2 meters long. So its packaging must be interesting. Okay, so understand, within the nucleus, 2.2 meters long DNA is well packed with least space. That is what we are going to discuss, packaging of DNA inside the cell. Okay, so come to the topic. So you have learned the length of, how many base pairs the bacterial cell, E. coli cells, Escherichia coli cells, DNA is about 1.36 millimeter. When it is converted to millimeters, it comes 1.36 millimeters. So if it's a bacterium, that means we can say if it's prokaryotic cells. In prokaryotes, first we discussed DNA packaging under two headings. How is DNA packaged in prokaryotes? How is DNA packaged in eukaryotes? Okay, in prokaryotes, you know that the cell is not having a definite nucleus. That is why they are prokaryotes. There is no true karyon. True nucleus is absent. Then instead, the genetic material, what you have learned earlier is, the genetic material is scattered. Okay, that is what you have learned earlier. It is in the form of supercoiled DNA. You have studied earlier. Okay, in prokaryotes, the genetic material is in the form of supercoiled DNA. We can say this DNA is arranged in a region known as, that also you have learned earlier, nucleoid. Okay, in prokaryotes there is no definite nucleus. Its genetic material, the DNA, is organized in a region called nucleoid. It means something less than a nucleus. Nucleoid means. Okay, so this region is known as, where the DNA is arranged, that region is known as what? Nucleoid. Then how the DNA is, how the genetic material is? It is in the form of a supercoiled DNA. Okay, if you see in a photograph, ultramicroscopic view, if you Google and see, you will wonder. I'll just post a picture for you. Okay, see, this way the DNA remains scattered inside a prokaryotic cell. For example, E. coli cell. What's the length of E. coli cell DNA? 1.36 millimeter. Okay, how are they packed? The DNA is seen in the form of scattered DNA, but well organized in a region called nucleoid. And this supercoiled DNA, how this is able to be packed like this? It is with the help of protein. It forms large loops with protein. Okay, this is the arrangement. In prokaryotes, the DNA arrangement we call large loops held by proteins. That is the arrangement of DNA or packaging of DNA in prokaryotes. Is it clear for you? Okay, how is DNA packaged in a prokaryotic cell? For example, a bacterium cell, E. coli. DNA is organized in a definite region called a nucleoid, no nucleus. Okay, then it is in the form of a supercoiled DNA. Here DNA can be seen as large loops held by protein. Okay, in order to pack, proteins are held. This is the packaging in prokaryotes, nothing in details. Then we are moving to the details of DNA packaging in eukaryotes. Next, packaging of DNA in eukaryotes. For example, in human cell. Okay, how is DNA packaged in a eukaryote? Okay, then you know in eukaryotic cell, okay, few micrometer size only, there is definite nucleus. Okay, then within the nucleus you might have drawn the DNA as a thread. Normally in interphase stage you have drawn DNA as threads. Do you remember? Everywhere you have drawn DNA as threads, and in lower classes you might have drawn some dots on this. Do you remember that? Okay, then this way, if it's DNA, in the form of a thread-like structure, we are calling it as chromatin. Okay, chromatin. Then in chromatin, or in most of the time, the cell is in the interphase. Okay, and most of the time DNA we can see as a thread-like material. How is DNA arranged in this level, chromatin level? Okay, if I draw this in a better way, this thread you can draw like this. Okay, just the beads like structure, the dots represented I can draw like this. Okay, then the beads, the thread. Okay, we can call it as beads on string. The structure is known as beads on string. Okay, I can again enlarge the view. Okay, then the structure will be like this. We can see the thread is wrapping around this. Okay, this is little more clear. That means the beads on string structure or chromatin level packaging of DNA. Okay, so listen carefully here. Inside the human cell or human nucleus, in the chromatin level packaging of DNA, DNA is arranged in the form of beads on string structure with the help of certain proteins. Okay, these proteins form an octamer molecule. That is what we observe as bead. You know, DNA is negatively charged. What is the charge of DNA? Negative. Why is DNA negatively charged? Because DNA consists of phosphoric acid, phosphate in every nucleotide. That gives DNA a negative charge. So, in order to bind this negatively charged DNA, there is positively charged protein. Okay? Now, how can the protein be charged? Why the positively charged protein is? This particular positively charged proteins are histone proteins. Why are histone proteins positively charged? Are all the proteins charged? Do the proteins have charge? Proteins are made up of what? Amino acids. You know, amino acids are neutral, basic, acidic. Like, if the amino acids are charged, proteins are charged. Okay, so histone proteins are made up of large number of basic amino acids. So, histone proteins are positively charged. Okay, the basic amino acids like lysine, arginine. Keep in mind these two names. Okay, most repeated question. So, histone proteins are rich in these two amino acids, lysine and arginine. What is special about these two amino acids? These two amino acids are basic amino acids. So, histone proteins are getting positive charge. So, understand, negatively charged DNA is packed with the help of positively charged histone proteins. That is what forms the beads on string structure. Is it okay? So, the next level, chromatin level packaging we are discussing how this beads on string structure. We are moving to the details of that. Keep in mind the charge of DNA is negative and charge of histone protein is what? Positive. Then when I draw this structure again enlarged, one structure enlarged. Okay, this is a unit of This is a unit of 8 histone proteins. Okay, there are 8 histone protein molecules to form one such a bead. Okay, so these 8 histone proteins are named as H2A, H2B, H3 and H4. 2 molecules each. Okay, 2 molecules each. What? H2A, H2B, H3 and H4 histone make this large unit. It is known as a histone octamer. So what is the bead? The bead is a histone octamer. What is an octamer? A unit of 8 molecules. Here which are the 8 molecules? 2 molecules H2A, 2 molecules H2B, 2 molecules H3 and 2 molecules H4. That all together form this bead-like structure. It is known as histone octamer. Okay, then I think it's clear. The histone octamer is. Then what is the structure? Next, what is charge of the histone octamer? It is positively charged. Why is it positively charged? Because it consists of large number of lysine and arginine basic amino acids. Okay. Then come to the structure. Here DNA is, what is the charge of DNA? What is the charge of DNA? DNA is negatively charged. You can see the negatively charged DNA is seen wrapped around this. Okay, negatively charged DNA is seen wrapped around this. Around 1.65 turns, correct measurement, about 1.65 turns. Okay, then listen. Okay, so now what you have drawn? A histone octamer along with, this is what histone octamer is, along with DNA. Okay, DNA is seen wrapped around the histone octamer. Is it okay? So understand, this structure altogether we can call as nucleosome. The unit is known as nucleosome. Is it okay? A unit of histone octamer along with the DNA wrapped around it. It is known as nucleosome. It can accommodate nearly 145 base pairs. Okay, then just understand, in your textbook you can see one more structure, that is another histone. Okay, see, this histone can link, it can act as a linker between this and the next one. Okay, this histone we can name as H1 histone. So how many different histones you have studied? 5 different histones. H1, H2A, H2B, H3 and H4. 5 different histones are used in DNA packaging. This as a linker. Okay, and here the DNA on either side of this we can call as linker DNA. And this nucleosome along with the linker DNA can accommodate nearly 200 base pairs. Okay, the nucleosome along with the linker DNA can accommodate nearly 200 base pairs. Such a full structure is known as a chromatosome. Okay, nucleosome along with the linker DNA with the H1 histone. Okay, the full structure we can call as chromatosome. Actually, the chromatosome is accommodating 200 base pairs. Okay, so is it clear for you? The structure of a nucleosome. Is it clear? So listen carefully here. The structure of nucleosome. May I repeat it? So in a human cell, within the nucleus, how is the DNA organized? You know, if the DNA is 2.2 meters long, can it be structured inside a nucleus? Impossible. 2.2 meters long, and this is only having a few micrometer radius. So it should be well packed within the nucleus. That packaging actually we discussed now, and it is well packed in a limited space by accommodating maximum base pairs in a beads on string structure in chromatin level. When it is chromatin, if it's chromosome level, it is again beyond the concept. Anyway, we will discuss it in a quick way. This beads on string structure. Actually, DNA is packed with the help of some positively charged proteins known as histones. Okay, about 8 molecules of histones form an octamer, a globular structure. It is known as histone octamer. Okay, it consists of 2 molecules each of H2A, H2B, H3 and H4. And around the histone octamer, you can see the DNA wrapped around. Okay, and that makes one nucleosome. I mean the histone octamer plus DNA makes one nucleosome. One nucleosome can accommodate nearly 145 base pairs. And when it is connected to the next nucleosome, there forms some free space, free DNA, we can call it as linker DNA, connected by H1 histones. H1 histones act as the linker, and it has linker DNA portions on either side. The nucleosome along with the linker DNA constitute chromatosome. Okay, usually chromatosome we consider as nucleosome itself. Okay, there is not much difference given in lower classes. You study it as nucleosome only. Anyway, it can accommodate nearly 200 base pairs. So you can imagine if 200 base pairs are stretched and kept, it requires more space. But if it is confined to a bead-like structure, it requires a limited space. That is the aim of this packaging. This way, the DNA is packed in a limited space within the nucleus. Is it okay for you? Now you know which are the different types of histones. Okay. Why are histones positively charged also you know. Okay. Then what is the difference between a nucleosome and histone octamer you know. Histone octamer consists of only protein. A nucleosome means protein plus DNA. Okay. Then listen to this. The next level structure. And when it comes to cell division, this is changing to what? Chromosome. Chromatin is changing to chromosome. Before that, see, the nucleosome can accommodate nearly 200 base pairs. And in the next level, chromatosome, you have studied 200 base pairs. Nucleosome, 145 base pairs. Then chromatosomes, about 200 base pairs. Okay. In the next level, that level just keep in mind, if it is asked for entrance or like questions, you can just answer. The next level is solenoid level. Solenoid structure. In solenoid structure, you can see circularizing of the beads on string structure. The beads on string structure is circularized. You can see circularized beads on string structure. Like just imagine it as a spring-like structure, circularized structure. And here about 6 nucleosomes can be seen in one ring. Likewise, I think in all the crockery shops you might have seen sack threads on a big axis and arranged in very tightly. You know how long the thread is? Okay, that way in a very limited space, very long thread is accommodated. Here in solenoid structure, one turn has about 6 nucleosomes. And likewise, just imagine around a central axis, this thing, the long thread, beads on thread, it is circularized. Then that packaging is known as solenoid. Just keep in mind that next level is solenoid level. Again, the next further in the chromosome level, when it comes to chromosome level, the structure is loop-like structure. The next level is called loop. Okay? First level, what is the first level? Chromatin level packaging is known as nucleosome. Then, second level, chromatosome level with linker DNA. Then, third level, solenoid level. Fourth level, loop. In the loop, just this type of solenoid, just imagine this solenoid is arranged in this loop. Okay, how many base pairs can be accommodated? Can you imagine? Okay, this type of solenoid is organizing into a loop. The circularized beads on string structure is organized into a loop. That is the loop level structure. Then the last level, again, you may wonder how is well packed. The last level is loop of loop. Okay, in loop of loop structure, that is, just listen. The loop is like this. I'll just draw it rough. Okay, this itself is having this package. That means this loop is organized to again this way. Can you imagine that? This loop is organized to this way. Loop of loop. That means this beads on string is forming. Then that space is enough to accommodate this long DNA. And this way we can just, and this is not given in your NCERT textbook, just have a look on the names. That's enough. Okay, this aim is to pack more more long DNA, more base pairs in a limited space. Okay, so that is about the packaging of DNA in chromatin level. Our next section, we have a small section. If is higher levels, if is chromosome level, it requires more condensation. You have studied this beads, this string-like structure with beads. This is known as chromatin. Okay, when it is cell division during metaphase, you have studied this undergo condensation to form what? Chromosome. Okay, these strings undergo condensation to form chromosomes. If it's a human cell, it undergoes this long thread, 2.2 meters long thread, undergoes condensation to form what? 46 chromosomes in a human cell. That you know. And if it's chromosome level packaging, this level packaging requires additional histone protein, additional proteins, not histone proteins. So chromosome level, this is chromatin level packaging. We have discussed beads on string structure with the nucleosome. Okay, with the histone proteins. If it's chromosome level packaging, in chromosome level packaging, it requires some additional proteins. These proteins are called non-histone chromosomal proteins. Okay, non-histone chromosomal proteins are also required. Along with the histone proteins, NHC proteins are also required for chromosome level, higher level packaging. And altogether, it's very well packed inside the nucleus. Okay, then understand, when we discuss about the chromatin, okay, some regions of chromatins, it's very highly condensed. Okay, more condensed. So it is dark stained. The region which is more condensed and dark stained is known as heterochromatin. The region of chromatin which is dense. Okay, the region of chromatin which is dense or dark stained is known as heterochromatin. Is the most condensed region, and this region has no role in protein synthesis. So they are not active in transcription. We will discuss transcription later. Okay, not active in transcription. Whereas the other region which is less condensed means loose. Okay, less condensed, loosely packed, it is known as euchromatin. The region of chromatin which is loosely packed is known as euchromatin. Okay, and keep in mind, euchromatin is involved in protein synthesis. This is transcriptionally active region. Okay, active region. That only about the DNA packaging. Towards the end, we discussed chromosome level packaging with NHC proteins, and also we discussed how to differentiate between heterochromatin and euchromatin, or transcriptionally active chromatin or transcriptionally inactive chromatin. A heterochromatin is a region of the chromatin material which is densely packed, so dark stained, and it cannot perform transcription translation by processes. We will discuss. Okay, what are these processes? Whereas euchromatin is loosely packed, okay, easy, it can do the transcription, and it is less stained also. So this is what I meant for today, and I think this concept is clear. If I have gone little fast, you have to just revise and see. Any more doubt means we will clear it later. Okay, thank you.